Hello, good people. Welcome to Unit 7. We're starting Unit 7, which is all about differential equations, and we're going to start with a fairly graspable, easy idea, and that is this. If I'm given a function graph, if I were to create tangent lines along this graph, and so I'm just picking some random points here along the graph, and I'm drawing the tangent lines on the curve of this graph. If I was able to take away and erase the curve, the question is, would you be able to tell what the original graph looked like just by, excuse me, just by looking at these red little lines? So if I was able to erase the original f of x curve, if I left these tangent lines, and the tangent lines again are just telling us the direction, the slope of the curve at that given point, would you be able to tell what the original graph looked like? And the answer is yes, because these little lines are telling you, oh, the graph is going up and then it's momentarily stopped and then it goes down and then it momentarily stops and then it goes up, right? So these red lines are little segments, I guess, of the tangent lines that are at those given points. This is the main idea behind slope fields. Slope fields, and some people call them directional fields, are a collection of tangent lines that really show you what the original function graph looks like. If you look closely at a slope field, you'll be able to see um, what the solution or the original graph looks like. And I'm going to skip ahead just a little bit just so that you can see what a slope field looks like. This is what a slope field looks like. And the slope field is really made up of a bunch of little tangent lines. And the question is, does this, if you kind of squint your eyes, if you kind of look at the direction of the lines, does it tell you what the original graph looks like? And the answer is yes, because in effect, the slope field is kind of like the blueprint of what the original function is. And so I'm going to go back because I want to make sure that you understand that a slope field is a graph of the slopes for a given function. And on the AP exam, you're going to be asked to do two things. One of the things you're going to be asked to do, or you could be asked to do, is to sketch a slope field. That's what we're going to practice in this video. And then the other thing you might be asked to do is to sketch the solution curve, sketch the original function through a given point if you have a slope field already created for you. So either you create the slope field or you use an already created slope field to draw a solution curve. And really, it's a sketch because not everything is exact, right? All right, so what do you need to know? You need to know that if you're given a differential equation, now we'll talk about this in a little bit. If you're given a differential equation, you can sketch the slope field at indicated points, excuse me, by just substituting, I apologize, by just substituting in the x and the y values into that differential equation. And you should know that on the AP exam, slopes on a slope field will never be undefined. So you're always going to have to draw a defined slope. Okay, so now let's talk about what is a differential equation, because this whole unit is about differential equation. Okay, so in example 1, we see an example of a differential equation. A differential equation is just an equation that involves a derivative. It could be the first derivative, it could be the second derivative. As long as the equation involves a derivative, that is a differential equation. But if you have a dy dx or an f prime y prime equation, then you have the slopes, and we're going to use this formula to figure out the slopes of these 6 points. So it says, consider this differential equation. On this axis provided, sketch a slope field for the given differential equation at the 6 indicated points. 1, 2, 3, 4, 5, 6. There's 6 points that are highlighted there. So what we're going to do is we're going to take each of those points, and then we're going to plug in that x and y value into the derivative function. And that derivative function is going to produce the slope at that given point. So we'll start with this one right here. So this point, my x coordinate is 1, my y coordinate is 1. But now I'm going to use this formula over here that says multiply 2 times your y value divided by your x value, and that's going to give you 2. So what does that mean? That means that I'm going to draw a little line segment that has a slope, because this is what this is, that has a slope of 2. All right, well, let me use my handy dandy ruler here. So how do I know where a slope of 2 is? It has to go through that point, but it has to have a slope of 2. Well, if I draw a line segment here, this goes up 2 over 1. Hey, I have a slope of 2. So I'm going to draw a little segment through there, and I'm done with the first one. I'm going to go to the next one. This point, I'm going to do an orange here. This point is 1, 0. So that means my dy dx, my slope, is 2 times my y value divided by my x value. Well, that's just 0. So I'm going to draw a line segment that has a slope of 0. And that's going to look like that. And I have my second point. And you keep doing that, right? The formula is going to tell you what the slope is, but you have to input the x and the y value. Okay, well, let's find the next x and y value. This one, dx is 1, the y value is negative 1. According to this formula, I'm supposed to multiply 2 times negative 1 divided by 1, and that's going to give me negative 2. So I have to find a slope. I have to draw a little line segment with slope 2. So this is a line segment of slope 1. This is a line segment of negative 1, I'm sorry. And this is a line segment of slope negative 2. How do I know that? Because it goes down 2 over 1. And so I draw my little line, and there is the completion of the first 3 points. What am I doing? I'm just finding the slopes at a given point, at a given x and y coordinate, and I'm using the differential equation. Since this is a derivative equation, it's giving me my slope at any given point, and if you know your x and y, well then substitute the x and the y value to get the slope. All right, let's go back to the other side. Negative 1 is my x, positive 1 is my y. I'm going to do the formula. 2 times y divided by x, that's going to give me negative 2. So I grab my ruler here, and I'm going to draw a line segment with slope negative 2. Down 2 over 1, got it. And I keep going. Negative 1, my y coordinate is 0. The formula says multiply 2 times your y divided by your x. That's going to give me 0. So this is going to be, this is going to be a flat line, a horizontal line, I should say, right there. And then the last one, x equals negative 1, y equals negative 1, multiply 2 times negative 1 divided by negative 1, and that just gives me 2. So now I need a slope of 2, so I'm going to align it this way. Why? Because this goes up 2 over 1, or up 2 over 1. So this will be, bam. I just created a slope field with just 6 points, right? They don't want me to build a complete slope field. And I did it by using this differential equation, this derivative equation that finds the slope for me, and it tells me what direction it's going to go. Common question from students: how accurate do I need to be? You saw that I was using a straight edge. I was using my ruler to align points in order to get a good slope. I don't think someone's going to sit there um, and measure each and every point to make sure you got the correct slope. And if you have points as references, use them to be as accurate as possible. All right, this next one. Consider the differential equation dy over dx equals y squared over x minus 1. On the axis provided, sketch a slope field for the given differential equation at the 10 points indicated. Oh, that's a lot of points. So I'm going to make a table over here for the ones on the right, and I'll make a table on the left for the other column of points on the y-axis. Okay, so let's start 2, 2. 2, 2. According to this, take your y-coordinate, square it, divided by x minus 1. So that's 4 over 1, and that's 4. So at this point right here, I need a slope of 4. That means, is that a slope of 4? Is this a slope of 4? 1, 2, 3. Oh, no, no, no. This is a slope of 4. Somewhere here, maybe? This goes 1, 2, 3, 4 up, and it goes 1 over. So 1 over, oh, rise over run, if you will. All right, got that one done. Next, x equals 2 and y equals 1. So that's 1 squared over 2 minus 1, and that's 1. Great. Align that this way. So this is the slope of rise 1 over 1. And I got, where'd it go? There's that. And then the next one, x2, y0. So that's y squared over 2 minus 1. Do you get a sense that if for all of these points where my x is 2, my denominator is always going to be 1. So from now on, I'm just going to do the numerator because along all of this column of points, my x value is always 2, and the denominator, therefore, 2 minus 1 will always be 1. So that's 0, flat. And then keep going. X equals 2, y equals negative 1. But remember what we said. The bottom is always going to be 1. So this is just 1. So I'm going to try to do something like this. And then at the next one, 2, negative 2, y squared over x minus 1. But that's just 1. So that's 4. And that gets me back to. Now at this point, I realize, hey, wait a minute. I already did one that has a slope of 4, which is up here. Why don't I just find that slant, that slope, and then just slide it this way, and we'll do something like that. Perfect? No, but we get the picture. And I'm not gonna do the other side, but you would see that the next side would be very similar. I'm not gonna do it here. I'll do it when I stop the video, and then I'll show you what it would look like. But maybe this could be a good opportunity for you to practice making the slope field for these points over here on the y-axis. Make a table if you want, and then just find the slope. That'll be something I'm going to ask you to do. All right, we're going to skip over to example 3. It says, while the slope field from example 2 is drawn at only 10 points, it is definitely defined at every point in the xy plane for which x does not equal 1. Why is it not defined at x equals 1? Oh, because if x was equal to 1, then I would have a 0 in the denominator, and that slope would be undefined. So there is no slope field at x equals 1, but every other point will have a slope. Describe all points in the plane where x is not equal to 1, for which dy dx equals negative 1. Okay, well, we know that dy dx is y squared over x minus 1, and I want that to equal negative 1. So the question is, can you find all the points in the plane where that's true? Well, if I multiply this denominator to the other side, if I do a little bit of algebra, I'm going to get 1 minus x. And then if I take the square root of both sides, I'm going to get y equals positive or negative square root of 1 minus x. And I just found all of the xy points that will produce a derivative, a dy dx, that's equal to negative 1. Which x and y points are there? Well, they're the ones that satisfy this equation, right? If y equals positive or negative square root of 1 minus x, then those x and y coordinates will produce a slope that is negative 1. And that's it. That's all you have to find. So the moral of the story here in video 1 is we are drawing slope fields. Slope fields are kind of the blueprint that tells me how the graph goes from left to right. And we're using the slope field as kind of like a blueprint of what the original function solution looks like. We're going to get more in depth into differential equations in the next section. But in this section, we're basically finding solutions to differential equations by just seeing these slope field maps or slope field blueprints of what they could look like.